The emptiness of space stretches outward in every direction, a darkness so vast and so complete that light itself seems to lose meaning across these distance points of matter. There is nothing here for millions of light years. No stars, no planets, no drifting clouds of gas. Only the silent vacuum of space extending further than the mind can comfortably hold. This is a cosmic void, one of the great empty regions that fill most of the universe, and somewhere within this darkness, a single galaxy drifts alone through the endless night. The galaxy is a spiral, much like our own Milky Way, with curving arms of stars and glowing nebulae wrapped around a bright central core of older suns. It spins slowly through the void, its billions of stars tracing their orbits around the galactic center, just as stars do in every spiral galaxy throughout the cosmos. But this galaxy has no neighbors, no companion galaxies visible in any direction, no gravitational dance partners to interact with across the millions of years of its existence. It exists in almost perfect isolation, surrounded by emptiness that would take light itself 100 million years or more to cross. This is the loneliest galaxy, or one of them, a cosmic island so far removed from other islands that the universe around it appears almost completely dark. From within this galaxy, looking outward past the glow of local stars, the sky would reveal an emptiness that observers in our own Milky Way have never experienced and cannot easily imagine. The void surrounding this galaxy is not merely empty by human standards, but empty by cosmic standards, underpopulated even compared to the already sparse regions that separate most galaxies. You are listening to The Drowsy Astronaut, and tonight we are taking a slow journey to the loneliest places in the universe. The void galaxies that drift through cosmic emptiness, far from any neighbor. This is not a journey that requires urgency or intensity, only a willingness to contemplate distances and timescales that dwarf anything in ordinary human experience, quietly and calmly. If you enjoy these journeys through the cosmos, consider leaving a comment about where you are listening from tonight, and perhaps a like if you find this helpful for rest. The emptiness we explore tonight has been waiting for billions of years, and it will wait patiently as we make our way through its mysteries together. The isolation of void galaxies differs fundamentally from the isolation that humans experience on Earth, which always remains connected to communities and ecosystems, even at its most extreme expressions. A person alone on a remote island is still on a planet with billions of other people, still within a solar system with other worlds, still within a galaxy containing hundreds of billions of stars. The loneliest galaxy experiences isolation on a scale that removes even these distant connections, existing so far from other galaxies that their light takes longer to arrive than human civilization has existed. Consider for a moment what isolation means when the nearest significant neighbor is 100 million light-years away, as it is for some of these void dwellers. Light traveling at 300,000 kilometers per second, the fastest speed anything can achieve in our universe, would need 100 million years to make that journey. A signal sent from such a galaxy toward its nearest neighbor would arrive long after the sender's star had likely burned out and died, long after generations of planets had formed and been destroyed, long after everything familiar had changed beyond recognition. The Milky Way, by contrast, exists in a relatively crowded neighborhood, with dozens of companion galaxies within just a few million light-years of our position in space. The Andromeda Galaxy, our nearest large neighbor, sits only 2.5 million light-years away, close enough that it appears as a smudge of light visible to the naked eye from dark locations on Earth. The large and small Magellanic Clouds, satellite galaxies orbiting our own, are even closer, visible from the southern hemisphere as cloudy patches in the night sky. We are surrounded by galactic company in a way that void galaxies simply are not. This companionship among galaxies is not merely aesthetic, but physically meaningful, as galaxies influence each other through gravity across the millions of light-years that separate them. The Milky Way and Andromeda are falling toward each other, drawn together by mutual gravitational attraction, and will eventually merge in about 4 billion years into a single larger galaxy. Our galaxy has already absorbed numerous smaller galaxies throughout its history, growing larger through these cosmic meals. Its structure, shaped by these interactions over billions of years. The void galaxy experiences none of this, evolving in isolation without external gravitational influences to shape its development. The gravitational isolation of void galaxies means they develop differently than galaxies in crowded environments, following their own internal dynamics, without interruption from outside forces. Their spiral arms remain undistorted by tidal forces from passing neighbors. Their gas remains unstripped by interactions. Their star formation proceeds at its own natural pace. They are like plants growing in a greenhouse with no wind, developing the forms that their internal genetics dictate, rather than being shaped by external environmental pressures over time. This undisturbed evolution makes void galaxies valuable to astronomers who want to understand how galaxies develop when left entirely to themselves, without external influence. Most galaxies we observe have been shaped by their environments, their properties reflecting not just their initial conditions, but also their history of interactions with neighbors. Void galaxies offer something closer to a controlled experiment, showing what happens when a galaxy forms and evolves without interference from the cosmic environment around it. The loneliness of these galaxies extends back to the earliest epochs of cosmic history, to the time when the universe was young and structure was just beginning to form from the primordial soup of matter and energy. The voids themselves began as regions slightly less dense than average, regions where there was marginally less matter in the early universe than in surrounding areas. Over billions of years, these small differences grew into the vast empty regions we observe today, as matter flowed out of the underdense regions and into the denser ones. The galaxies that remain in voids today are those that formed early enough to establish themselves before most matter had drained away toward denser regions elsewhere in the cosmic web. They are survivors of a sort, inhabitants of a landscape that has been slowly emptying for most of cosmic history, watching their environment grow ever more sparse as time passes. Their isolation was not sudden but gradual, developing over billions of years as the cosmic web took shape around them and they found themselves in the spaces between the strands. The void galaxy continues its slow rotation through the darkness, its stars orbiting, its gas clouds occasionally collapsing to form new stars as they have for billions of years. Nothing disturbs this quiet process. No gravitational tugs from passing galaxies, no streams of intergalactic gas falling in from cosmic filaments, no satellite galaxies being absorbed into the larger structure. The galaxy exists in a state of cosmic peace, undisturbed and unchanged by external events, for timescales that dwarf everything in human experience and comprehension. Darkness surrounds the galaxy on every side, the void extending outward for distances that would take light longer to cross than life has existed on Earth in any form. The nearest galaxy is so far away that its light, if visible at all, would appear as the faintest possible smudge, a ghostly presence at the very limit of detection, even with the most powerful telescopes. The isolation is nearly complete, broken only by the thin presence of intergalactic gas and the faint glow of the cosmic microwave background radiation that fills all of space. Within the galaxy itself, life would be possible, at least in principle, on planets orbiting stable stars, just as life is possible in our own Milky Way. An intelligent species arising on such a world would look up at their night sky and see the stars of their home galaxy, much as we see our own Milky Way stretching across Earth's night sky. But looking beyond their galaxy, into the intergalactic darkness, they would find almost nothing. A void so empty that the universe itself might seem far smaller and lonelier than it actually is. This perspective from within a void galaxy would shape how its inhabitants understood the cosmos, at least until they developed telescopes powerful enough to detect the distant walls of galaxies surrounding their void. They might initially believe their galaxy was all that existed, a single island of light in an infinite darkness, unaware that beyond the void, the universe teems with hundreds of billions of other galaxies. The discovery that they were not alone, that the emptiness around them was merely local rather than universal, would be a revelation of almost incomprehensible magnitude. The loneliest galaxy drifts onward through its void, patient and unhurried, its stars shining into the darkness without any nearby observer to appreciate their light, except possibly itself. It has existed in this state for billions of years and will continue for billions more. Its isolation, a permanent feature of its cosmic address, rather than a temporary condition. The universe is mostly empty, and this galaxy has made its home in the emptiest regions of all, a solitary presence in the vast cathedral of cosmic structure. From within this lonely galaxy, looking outward, the view reveals the true nature of the void in ways that no external observation could fully capture or communicate. The experience of that darkness, that absence, that vast surrounding nothing, belongs uniquely to whatever observers might exist within these isolated systems. The sky they would see tells a story of cosmic loneliness that our own busy neighborhood can only hint at through careful astronomical measurements and theoretical models. The night sky from within a void galaxy would begin much as our own night sky begins, with the familiar presence of nearby stars scattered across the darkness in patterns both random and beautiful. The stars of the home galaxy would shine down from whatever heavens existed on worlds orbiting those distant suns, points of light varying in brightness and color, just as stars do in our own sky. This local stellar backdrop would feel familiar, even comforting, to any observer who had grown up beneath it across the generations of their species. The band of the home galaxy would stretch across the sky, a river of light composed of billions of unresolved stars, too distant to separate with the naked eye, but bright enough collectively to create a glowing path through the darkness. This galactic band would curve overhead, much as our own Milky Way curves overhead on clear, dark nights away from city lights on Earth. An observer in a void galaxy would see their home galaxy from the inside, just as we see ours, a perspective that reveals the flat disk structure of spiral galaxies through direct visual experience. Beyond this familiar galactic glow, however, the view would diverge dramatically from what observers in our own Milky Way experience when looking into the depths of space beyond our local stellar neighborhood. Here, where our sky reveals the soft smudge of the Andromeda Galaxy and the cloudy forms of the Magellanic Clouds, the void galaxy observer would find almost nothing at all. The intergalactic space surrounding their home would reveal itself as truly and deeply empty, a darkness unbroken by neighboring galaxies. From Earth, the Andromeda Galaxy is visible to the naked eye as a faint, elongated smudge in the constellation that gives it its name, recognizable once you know where to look for it. This neighboring spiral galaxy, containing perhaps 1 trillion stars, spans several degrees of our sky, despite being 2.5 million light-years distant from our position. It represents the most distant object visible to human eyes, without telescopic aid, a connection to cosmic scales that observers have noticed since ancient times. The Void Galaxy Observer would have no such neighbor to observe, no convenient nearby galaxy to serve as a stepping stone toward understanding the larger universe that exists beyond their local void. Their nearest significant neighbor might be 100 million light-years away, 40 times farther than Andromeda is from us, far too distant to detect without sophisticated instruments. The intergalactic sky would appear perfectly dark, revealing nothing of the cosmic web that surrounds their void at such tremendous distances. This darkness beyond the home galaxy would shape the early astronomy of any civilization arising within a void galaxy in ways that might delay their understanding of cosmic structure significantly. Without obvious neighboring galaxies to observe, the questions that drove early cosmology in human history might never arise, or might arise much later and in different forms. The very concept of other galaxies might remain purely theoretical until technology advanced enough to detect the faint, distant walls of galaxies surrounding their empty home. The Magellanic Clouds that grace southern skies on Earth, dwarf satellite galaxies orbiting the Milky Way, would also be absent from the void galaxy sky in almost every case. Void galaxies typically lack satellite companions because they formed in regions too sparse to produce the swarms of smaller galaxies that orbit larger ones in denser environments. The void galaxy would be alone not just at the large scale, but at the small scale as well, without even tiny companion galaxies to provide hints of structure beyond its borders. An observer in such a galaxy who developed a telescope and began systematically scanning the sky would find their search for other galaxies initially frustrating and possibly confusing. Where our telescopes reveal thousands of galaxies in every deep exposure, their telescopes might reveal only darkness, punctuated by the occasional, very faint and very distant galaxy, barely detectable at the limits of their instruments. The universe would appear much emptier than it actually is, a perspective created by the accident of their cosmic address. Eventually, with powerful enough telescopes and long enough exposures, the void galaxy astronomers would detect the walls and filaments of galaxies that bound their void at distances of tens of millions of light-years or more. These detections would reveal that their galaxy was not alone in the universe, but merely isolated, surrounded by a vast bubble of emptiness, bounded by structures containing countless other galaxies. The discovery would transform their understanding of the cosmos, revealing that their experience of isolation was local rather than universal. The cosmic microwave background radiation would still be visible to sophisticated instruments within a void galaxy, the faint afterglow of the hot early universe that permeates all of space, regardless of local density. This radiation would provide evidence of cosmic history and structure, even to observers in the emptiest regions, connecting them to the larger story of the universe's evolution. The void galaxy would still be part of the cosmos, still embedded in the same physical laws and cosmic history, despite its isolation. Looking toward the walls of galaxies that bound their void, the void galaxy astronomers would observe structures that exist at tremendous distances from their position within the empty interior. The light reaching them from these walls would have traveled for tens of millions of years or more, representing ancient views of galaxies as they existed in the distant past. The walls would appear as faint concentrations of distant light, hints of the cosmic web that surrounds but does not penetrate their empty home. The redshift of light from these distant walls would reveal the expansion of space between the void galaxy and the surrounding structures, the stretching of wavelengths that occurs as light travels through expanding space. This cosmological redshift would be measurable with appropriate instruments, confirming that the universe is expanding and that the void galaxy's isolation is growing greater over time. The walls are receding, carried away by the expansion of space itself, leaving the void galaxy ever more alone. The psychological impact of this cosmic view might differ from civilization to civilization, but the physical facts would remain the same regardless of who observed them. The void galaxy exists in genuine isolation, surrounded by emptiness that separates it from the nearest significant concentrations of matter by distances that dwarf the galaxy itself many times over. This isolation is visible in the sky, readable in the absence of nearby galaxies that observers in denser regions take for granted. The darkness surrounding the void galaxy is not the darkness of true emptiness, but the darkness of extreme dilution, space that contains far less matter than average, but is not completely devoid of content. Traces of intergalactic gas exist even in voids, along with dark matter and the ever-present cosmic microwave background radiation. But these subtle presences do little to fill the void's apparent emptiness, which remains a defining feature of the region and the galaxies it contains. Stars within the void galaxy would continue to be born from collapsing gas clouds, live out their lives, fusing hydrogen into heavier elements, and eventually die in various ways, depending on their masses. This stellar life cycle would proceed normally despite the cosmic isolation, driven by local physics rather than galactic environment. The void galaxy would remain vibrant internally even as it drifted through the external emptiness, a living system surrounded by non-living space. The view from the void galaxy teaches something important about cosmic structure, revealing through direct visual experience the vast emptiness that fills most of the universe's volume. Voids are not exceptional regions, but rather the dominant feature of cosmic geography, comprising far more space than the walls and filaments where most galaxies gather. The void galaxy's perspective is, in a sense, the more typical perspective on the universe, the view from the empty majority rather than the crowded minority. From this lonely vantage point, the universe appears as it truly is at the largest scales, mostly empty, with occasional concentrations of matter separated by vast gulfs of nearly perfect vacuum. The cosmic web that we observe from our position in a relatively dense region looks different from within the voids, its structure apparent only as distant walls rather than as a surrounding network of connected filaments. The isolation is real, visible, and permanent, a defining feature of the void galaxy's existence throughout cosmic time. The view continues outward from the void galaxy into the darkness that surrounds it, the emptiness that extends for millions of light years before encountering the first hints of other concentrations of matter. This void, one of many that fill the universe, represents one of the largest coherent structures in the cosmos, a bubble of low density bounded by walls and filaments of higher density, where galaxies cluster together. Understanding these voids requires stepping back to see the larger cosmic structure of which they form such a significant part. The cosmic voids that isolate these lonely galaxies represent the largest structures known to exist in the universe. Vast bubbles of emptiness, spanning tens of millions to hundreds of millions of light years across their diameters. These are not merely regions with slightly fewer galaxies than average, but genuinely underdense spaces where the galaxy count drops to perhaps 1/10 or 1/20th of the cosmic norm. The voids dominate the universe by volume, comprising roughly 80% of all space, while containing only a small fraction of all matter. A typical cosmic void might span 50 million light years from one side to the other, a distance so vast that light itself needs 50 million years to cross it completely. Larger voids exist as well, supervoids stretching for hundreds of millions of light years, some approaching or exceeding 1 billion light years in their greatest dimensions. These are not subtle variations in cosmic density, but dramatic, empty regions that punctuate the universe like bubbles in cosmic foam. The Boötes void provides one of the best studied examples of these great empty regions, a roughly spherical bubble of low galaxy density, located in the direction of the constellation Boötes, from our perspective on Earth. Spanning approximately 330 million light-years across, the Boötes void contains only about 60 known galaxies, despite its enormous volume, a population that would fit comfortably in a region a tiny fraction of its size, in denser environments. The void was discovered in 1981 and initially seemed so empty that astronomers questioned whether such vast underdensities could actually exist. The name void accurately captures the essential character of these regions, their defining quality of having far less matter than comparable volumes elsewhere in the universe contain. The voids are not completely empty, as they contain thin wisps of intergalactic gas, dark matter, and the rare void galaxies that form the subject of our journey tonight. But compared to the walls and filaments that surround them, the voids are dramatically underpopulated, gaps in the cosmic web rather than nodes or strands. Understanding the shape of voids requires visualizing the universe as a three-dimensional structure rather than the two-dimensional maps that often represent cosmic surveys visually. The voids are roughly spherical or ellipsoidal in shape, like bubbles in foam, bounded on all sides by the walls and filaments where most galaxies concentrate together. They stack and nest against each other, filling the universe with their emptiness, while galaxies crowd into the thin boundaries between them. The cosmic foam analogy helps capture the overall structure of the universe at its largest scales, with voids playing the role of the air pockets within soap foam, and galaxy-filled walls playing the role of the soap film between bubbles. Just as foam consists mostly of air with thin films of soap separating the bubbles, the universe consists mostly of voids with thin walls and filaments of galaxies separating the empty regions. The matter content of the universe concentrates in these thin structures, while the voids contribute mostly volume with little mass. The walls that bound voids are themselves interesting structures, sheet-like concentrations of galaxies that separate adjacent voids from each other across their boundaries. These walls contain thousands or millions of galaxies spread across surfaces that might span hundreds of millions of light years, while remaining relatively thin compared to their extent. The Great Wall, discovered in galaxy surveys, represents one such structure, a vast sheet of galaxies that extends for hundreds of millions of light years across the cosmic map. Filaments represent another structural component of the cosmic web, elongated strands of galaxies that connect the denser regions where walls intersect, and clusters form at the nodes. These filaments thread through the universe like the strands of a spider web, providing paths along which galaxies can migrate over cosmic time as gravity draws them toward denser regions. The filaments are less dense than the walls, but far denser than the voids they traverse. Galaxy clusters form at the intersections of filaments and walls, the densest concentrations of galaxies in the universe outside the cores of individual galaxies themselves. These clusters can contain thousands of galaxies packed into regions just a few million light years across. Enormous, gravitationally bound structures, far removed from the isolation that void galaxies experience. The Virgo cluster and the Coma cluster represent well-studied examples of these dense galactic congregations. The void galaxies exist in the opposite extreme of cosmic density, isolated within the empty bubbles, rather than gathered in the crowded intersections of the cosmic web structure. Their isolation is not absolute, as even voids contain some galaxies scattered through their interiors. But the distances between void galaxies dwarf the distances between galaxies in clusters, or even in the general field population. A void galaxy might be the only significant concentration of matter for tens of millions of light years in any direction from its position. The distribution of matter into this web-like structure developed over billions of years through the action of gravity on the tiny density variations present in the early universe shortly after the Big Bang occurred. Regions that started slightly denser than average attracted matter from surrounding space, growing denser still as gravity amplified the initial differences over cosmic time. Regions that started slightly less dense lost matter to their denser neighbors, becoming ever emptier as the cosmic web took shape around them. The voids we observe today are the descendants of those primordial underdensities, regions that began with slightly less matter than average and have been losing matter to surrounding structures ever since the universe began expanding. They have grown emptier over time, their boundaries expanding outward as matter continues to flow toward the denser walls and filaments that surround them. The void galaxies that remain within these regions are those that formed early enough to establish themselves before the exodus of matter was complete. The scale of cosmic voids becomes clearer when compared to more familiar astronomical distances that provide reference points for the mind to grasp. The Milky Way galaxy is about 100,000 light-years across, making it a substantial structure by any reasonable standard of measurement. A typical cosmic void might span 500 times this distance, large enough to contain thousands of galaxies like our own, if it were as dense as our local region of space. Instead, such a void might contain only a handful of scattered galaxies, lost in the enormous volume. The boundaries between voids and the surrounding cosmic web are not sharp edges, but gradual transitions where galaxy density slowly increases as one moves from void interior toward wall or filament. The void edge is not a wall, but a gradient, a region where isolation gives way to company over distances of millions of light years of gradual change. Void galaxies near the edges of their voids are less isolated than those near the centers, experiencing some gravitational influence from the approaching wall, even if not yet part of it. The very existence of these vast, empty regions tells us something important about the nature of the universe and the processes that shaped it over cosmic time. The universe is not uniformly filled with matter, but highly structured, organized into patterns that reflect the physics of gravitational collapse, acting on primordial fluctuations. The voids are as much a part of this structure as the galaxy clusters, defining the cosmic web through their emptiness as surely as the walls define it through their density. The cosmic voids continue their slow expansion as the universe evolves, growing larger as space itself stretches, and as matter continues flowing toward denser regions over timescales of billions of years. The future universe will be even emptier than the present one, with voids growing larger and walls becoming more attenuated as dark energy drives accelerating expansion. The void galaxies that exist today will become ever more isolated as the cosmic web stretches and thins around them. Within these great empty regions, the rare void galaxies continue their quiet existence, forming stars and spinning through the darkness without the interactions that shape galaxies in denser environments significantly. They are the inhabitants of the cosmic gaps, the dwellers in emptiness, surrounded by the structures that contain most galaxies, but separated from those structures by distances that isolate them almost completely from external influence. Most galaxies do not experience the isolation that defines void dwellers, but instead exist within the cosmic web, surrounded by neighbors and connected to larger structures through gravity and shared motion. The Milky Way provides an excellent example of this more typical cosmic situation. A galaxy embedded in a network of companions, clusters, and superclusters that stretches across hundreds of millions of light years of space. Understanding this normal galactic environment helps clarify what makes void galaxies so exceptional. By comparison, the local group is the name astronomers give to the small cluster of galaxies that contains the Milky Way, along with about 80 other galaxies spread across a region roughly 10 million light-years in diameter. This modest collection includes the Andromeda Galaxy, our nearest large neighbor, along with the Triangulum Galaxy and numerous dwarf galaxies that orbit the larger members as satellites. The local group is gravitationally bound, meaning its member galaxies will remain associated with each other rather than drifting apart as the universe expands. The Andromeda Galaxy dominates the local group, along with our own Milky Way, the two largest members whose mutual gravitational attraction will eventually bring them together in a merge of billions of years in the future. At 2.5 million light-years distant, Andromeda represents the most distant object visible to the naked eye, a smudge of light that actually comprises 1 trillion stars in a spiral structure similar to our own galaxy. The Void Galaxy Observer has no such neighbor to observe, no comparable smudge of light revealing the presence of another major galaxy. The satellite galaxies of the Milky Way add further texture to our galactic neighborhood. Small companion galaxies that orbit our larger galaxy like moons orbiting a planet in miniature form. The Large and Small Magellanic Clouds are the most prominent of these satellites. Irregular dwarf galaxies visible from the southern hemisphere as cloudy patches in the night sky. Dozens of other dwarf galaxies orbit the Milky Way, some discovered only recently through careful surveys that revealed their faint populations of ancient stars. These satellite galaxies influence the Milky Way and are influenced by it in turn, their orbits shaped by its gravity, while they contribute small gravitational tugs of their own that affect its structure over time. Some satellites are being torn apart by tidal forces as they pass too close to the Milky Way's center, their stars strung out in streams that will eventually be absorbed into our galaxy. The Void Galaxy typically has no such satellites to interact with, existing alone without the retinue of smaller companions that characterizes galaxies in denser environments. The local group itself belongs to a larger structure called the Virgo supercluster, a vast concentration of galaxies and galaxy groups centered roughly on the Virgo cluster, about 50 million light-years from our position. The Virgo cluster contains over 2,000 galaxies packed into a region just a few million light-years across, a density of galaxies that dwarfs anything the Void Galaxy experiences. Galaxies in and near the cluster interact constantly, their gas stripped by hot intra-cluster medium and their structures distorted by frequent gravitational encounters. Beyond the Virgo supercluster lies an even larger structure called Laniakea, the supercluster of superclusters that contains our cosmic address, along with perhaps 100,000 other galaxies spread across 500 million light-years. The Laniakea supercluster represents the largest structure to which the Milky Way belongs, a vast, coherent region where galaxies flow together toward a gravitational attractor called the Great Attractor, located deep within its interior. The cosmic web that contains these structures extends throughout the observable universe, connecting superclusters and clusters through filaments and walls that span billions of light-years in total extent. This web represents the largest scale organization of matter in the cosmos, the skeleton on which galaxies hang like ornaments throughout the universe's volume. The voids occupy the spaces between the web's strands, the empty bubbles that fill most of the universe's volume while containing little of its matter. Galaxies within the cosmic web experience a fundamentally different existence than void galaxies, shaped by their environment in ways that isolation prevents entirely. Cluster galaxies in particular undergo transformations driven by their dense surroundings, their star formation often quenched by the removal of cold gas through various environmental processes. The hot gas that fills galaxy clusters can strip colder gas from galaxies that pass through it, effectively cutting off the fuel supply for new star formation. Gravitational interactions between galaxies in the cosmic web reshape their structures over time, stretching spiral arms, triggering bursts of star formation, and sometimes leading to complete mergers that transform two galaxies into one. The Milky Way shows evidence of past interactions in the streams of stars that trace the orbits of consumed dwarf galaxies. And it will experience a major interaction when it merges with Andromeda in the distant future. The void galaxy avoids all such interactions, evolving in isolation without external forces to shape its development. The contrast between the crowded cosmic web and the empty voids represents one of the most fundamental features of cosmic structure, the division of space into regions of high and low density that has persisted since the early universe and will continue indefinitely into the future. The void galaxies experience this structure from the empty side, looking outward at walls of distant galaxies, rather than inward from within the walls themselves. Their perspective on the universe differs from ours as a result. The motion of galaxies within the cosmic web reveals its gravitational influence, as galaxies flow along filaments toward the denser regions where clusters form at the intersections of multiple strands. This cosmic flow carries galaxies through space at hundreds of kilometers per second relative to the overall expansion of the universe, drawn by gravity toward the concentrations of mass that anchor the web. Void galaxies participate in this flow to a lesser extent, drifting slowly away from the void centers toward the distant walls as matter continues to evacuate the empty regions. The cosmic web also contains gas that has never formed into galaxies, a tenuous medium that threads through the filaments and walls, providing fuel for star formation in galaxies that encounter it along their paths. This intergalactic gas is too thin and too hot to observe directly in most cases, but its presence is inferred from absorption lines in the spectra of distant quasars, whose light passes through it. The voids contain less of this gas than the web, another aspect of their emptiness that distinguishes them from denser cosmic environments. Understanding the contrast between void environments and web environments helps explain why void galaxies differ from their counterparts in denser regions, their properties reflecting their isolated circumstances rather than external influences. The environmental dependence of galaxy properties represents an active area of astronomical research, with void galaxies providing a crucial comparison sample for understanding how environment shapes galactic evolution. The cosmic web will continue to evolve over billions of years, with matter flowing from voids toward walls and filaments, and from filaments toward clusters at the nodes where multiple strands meet. This flow concentrates matter ever more strongly in the densest regions, while leaving the voids ever more empty, a process that has been ongoing since the universe was young and will continue far into the future. The void galaxies will become more isolated still as this evolution progresses. The structure of the cosmic web arose from processes that operated in the early universe, when tiny fluctuations in the density of matter provided the seeds that gravity would amplify into the vast structures we observe today. Understanding how the voids formed requires looking back to these early times, when the universe was young and smooth, and the great empty regions of today were just subtle underdensities, waiting to be excavated by the flow of cosmic matter toward denser regions. The emptiness of cosmic voids did not always exist, but developed gradually over billions of years, from subtle variations in the early universe's density that gravity amplified into the vast structures we observe today. In the beginning, shortly after the Big Bang, the universe was remarkably smooth, with matter distributed almost uniformly throughout space in a hot, dense state that showed only the faintest hints of the structure that would eventually develop. The voids and walls of today were written in those tiny variations, waiting to be revealed as gravity did its patient work across cosmic time. The cosmic microwave background radiation preserves an image of the universe as it appeared about 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. This radiation shows the universe at that epoch as almost perfectly uniform, with temperature variations of only about 1 part in 100,000 across the entire sky. These tiny temperature differences correspond to equally tiny density differences, regions with slightly more or slightly less matter than the cosmic average. The regions that would become voids were those that started with slightly less matter than average, perhaps only a fraction of a percent below the cosmic mean density in those early times. This small deficit was enough to change their fate over the billions of years that followed, as gravity drew matter away from these underdense regions and toward the denser regions that would become walls and filaments. The voids did not empty out suddenly, but gradually, losing matter to their denser surroundings over timescales measured in billions of years. The physics of this process is straightforward, even if the timescales are difficult to comprehend fully. Gravity attracts matter toward regions of higher density, causing those regions to grow denser still while depleting the surrounding underdense areas. A region that starts with 1% less matter than average will lose additional matter to its surroundings, becoming ever more underdense as time passes and gravity continues to operate. The rich get richer while the poor get poorer, a cosmic Matthew effect playing out across the universe's entire volume. Dark matter played a crucial role in this process, providing most of the gravitational pull that shaped the cosmic web and excavated the voids over cosmic history. Dark matter does not interact with light or ordinary matter, except through gravity, but it outweighs ordinary matter by roughly 5-to-1 in the universe's mass budget. The dark matter began collapsing first, forming the gravitational scaffolding on which ordinary matter would later accumulate to form galaxies and clusters. The first structures to form were small concentrations of dark matter called halos, gravitationally bound clumps that attracted ordinary matter into their centers, where it could cool and form stars. These early halos were the seeds of future galaxies, the sites where star formation would begin as the universe aged and matter concentrated into denser and denser structures. The halos formed preferentially in the denser regions that would become walls and filaments, leaving the void regions with fewer of these early structures. Galaxies that formed in the proto-void regions did so early, before the exodus of matter had significantly depleted these areas of the raw material needed for galaxy formation. These early void galaxies would become the ancestors of the isolated systems we observe today, surviving within the voids as their surroundings emptied out around them. They represent a sparse population of early formers, galaxies that established themselves before their neighborhoods became uninhabitable for new galaxy formation. The expansion of the universe also contributed to the growth of voids, stretching the already underdense regions faster than they could accumulate matter from their surroundings through gravitational attraction. Space itself was growing, and the voids were growing with it, their boundaries expanding outward even as matter flowed away from their centers toward the surrounding walls. This expansion has accelerated in recent cosmic history due to dark energy, the mysterious force that is pushing the universe apart at an ever-increasing rate. Dark energy affects voids more strongly than denser regions because the gravitational binding of matter is weaker in the underdense void environments than in the overdense walls and clusters. In the densest regions, gravity can resist the expansion of space and hold structures together despite the outward push of dark energy. In voids, where matter is sparse and gravity is weak, dark energy dominates, and the expansion proceeds faster than in denser environments. The result is that voids have been growing larger over cosmic time, their boundaries expanding outward as space stretches and as matter continues flowing toward the denser regions at their edges. The voids today are larger than they were 1 billion years ago, and they will be larger still 1 billion years in the future as this process continues. The isolation of void galaxies is increasing over time, their distance from the nearest walls and filaments growing as the cosmic web stretches. The formation of cosmic structure from the nearly uniform early universe represents one of the great successes of modern cosmology, with observations matching theoretical predictions to remarkable precision across a wide range of scales. Computer simulations that model the gravitational evolution of matter from early times to the present day produce virtual universes that closely resemble the real one, complete with voids, walls, filaments, and clusters in the correct proportions and arrangements. These simulations help astronomers understand the history of individual void galaxies, tracing their origins back to the early universe and following their evolution through billions of years of cosmic time. The simulated void galaxies form early and evolve in isolation, matching the properties observed in real void galaxies that have been studied through telescopic observation. The agreement between simulation and observation supports our understanding of how cosmic structure formed and evolved. The void galaxies that exist today are thus the products of specific cosmic histories, formed in regions that were destined to become empty and surviving as isolated systems, while their surroundings lost most of their matter to denser regions elsewhere. Their isolation is not accidental, but a direct consequence of where they formed in the density field of the early universe. A fate written in the tiny fluctuations imprinted during the first moments of cosmic history. The emptiness surrounding void galaxies has been growing since the universe was young, and it will continue growing into the far future as dark energy drives accelerating expansion and matter flows toward ever denser concentrations. The void galaxy of today experiences profound isolation, but the void galaxy of the far future will be more isolated still, its surroundings stretched to even greater emptiness by the relentless expansion of cosmic space. Understanding how emptiness forms helps explain why void galaxies have the properties they do, evolving in isolation without the external influences that shape galaxies in denser environments throughout the cosmic web. The void galaxy has grown up alone, developing according to its own internal dynamics, rather than responding to gravitational tugs and gas flows from its cosmic neighborhood. This isolated development produces distinct characteristics that distinguish void galaxies from their counterparts elsewhere in the universe. The isolation of void galaxies extends throughout their entire histories. shaping their evolution from the earliest epochs of galaxy formation to the present day without the external influences that mold galaxies in crowded environments. A galaxy in a cluster or filament experiences constant interaction with its surroundings, gravitational encounters with neighbors, flows of gas from the intergalactic medium, and occasional mergers that can transform its structure entirely. The void galaxy experiences none of this, developing according to its own internal physics without external interference of any significant kind. This undisturbed evolution makes void galaxies natural laboratories for understanding how galaxies develop when left entirely to themselves, free from environmental influence. Most galaxies show the marks of their cosmic neighborhoods, properties shaped by interactions and accretion that obscure the signatures of pure internal evolution. Void galaxies offer something closer to a controlled experiment. Isolated systems whose properties reflect their own physics rather than the accidents of their environments. Galaxy mergers represent one of the most dramatic processes that void galaxies avoid through their isolation. The collisions and combinations that transform galaxy structure and trigger intense bursts of star formation. When two galaxies merge, their combined gravity draws them together over millions of years, distorting their shapes before finally combining into a single larger system. The stars in merging galaxies rarely collide directly, but the gas clouds do, compressing and heating to trigger rapid formation of new stars throughout the combined system. The Milky Way has experienced numerous minor mergers throughout its history, absorbing smaller dwarf galaxies that wandered too close and were torn apart by tidal forces. Evidence for these past mergers appears in streams of stars that trace the orbits of consumed galaxies, still recognizable even after billions of years as distinct structures within our galaxy's halo. The Milky Way will experience a major merger when it combines with Andromeda in roughly 4 billion years, an event that will transform both galaxies dramatically. Void galaxies have never experienced significant mergers and likely never will, at least not until the very distant future, when cosmic evolution might bring them into contact with other structures. Their stellar populations and structures reflect uninterrupted evolution, shaped only by internal processes like star formation and stellar death without the external triggers that mergers provide. They have grown only through the gradual accretion of gas from their immediate surroundings, never through the absorption of other galaxies. Gravitational interactions, short of actual merger, also shape galaxy structure in dense environments. Tidal forces from passing neighbors, stretching and distorting galaxies that would otherwise maintain their pristine shapes. A galaxy passing through a cluster experiences gravitational tugs from many directions, its outer regions pulled and stretched by the collective gravity of thousands of other galaxies in close proximity. These tidal interactions can strip stars from the galaxy's outskirts and reshape its disk into distorted configurations. The void galaxy experiences no such tidal influence. Its nearest neighbor so distant, the gravitational effects are entirely negligible over any reasonable timescale. Its structure reflects pure internal dynamics. The rotation of its disk, the gravity of its dark matter halo, and the motions of its stars following orbits determined solely by the galaxy's own mass distribution. The void galaxy is a closed system to a degree that cluster galaxies can never approach. Gas accretion from the intergalactic medium also differs between void galaxies and their counterparts in denser environments, affecting the fuel supply available for star formation over cosmic time. Galaxies in filaments and walls receive flows of fresh gas from the surrounding cosmic web, material that can sustain star formation for billions of years beyond what the galaxy's initial gas supply would allow. This cosmic accretion feeds galaxy growth in crowded regions. Void galaxies have less access to this external gas supply. Surrounded by the sparse intergalactic medium of the void, rather than the richer flows available in denser regions, they must rely more heavily on their internal gas reservoirs, recycling material through stellar death and supernova explosions to maintain star formation over cosmic time. Despite this, void galaxies often maintain higher gas fractions than cluster galaxies, perhaps because nothing has stripped their gas away. The hot gas that fills galaxy clusters represents another environmental influence absent from the void galaxy experience, a medium that can remove cold gas from galaxies through a process called ram pressure stripping. When a galaxy moves through the hot intra-cluster medium, the pressure of the gas it encounters can blow the colder gas out of its disk, much like wind blowing leaves from a tree. This stripping cuts off the fuel supply for star formation, quenching the galaxy. Void galaxies never encounter this hot medium because no clusters exist in their vicinities, and the intergalactic gas of the void is far too thin to exert significant ram pressure on passing objects. Their cold gas remains intact, available for star formation indefinitely without external processes to remove it. This preservation of gas may explain why void galaxies tend to be bluer than cluster galaxies, still forming stars, while many cluster galaxies have gone quiet. The evolution of void galaxies thus proceeds according to internal timescales rather than external triggers, star formation continuing as gas gradually converts to stars and is recycled through stellar death. Supernova explosions drive gas out of star-forming regions, but not out of the galaxy entirely. And this ejected gas can cool and return to form new stars over timescales of millions of years. The cycle continues indefinitely, without the interruptions that dense environments provide. Stellar populations in void galaxies may therefore differ from those in cluster galaxies of similar mass, reflecting the different evolutionary histories that isolation versus crowding produce over cosmic time. Void galaxies tend to have younger, average stellar populations, more ongoing star formation, and bluer colors that indicate recent star formation activity continuing to the present day. They are still building themselves, while many cluster galaxies finished their star formation billions of years ago. The structures of void galaxies also remain more regular than those of galaxies in dense environments, their spiral arms unperturbed by tidal interactions, their disks thin and extended without distortion from encounters. A void spiral galaxy looks like a textbook example of spiral structure, the ideal form that rotation and gravity produce, without external complications to muddy the picture. This pristine quality makes void galaxies valuable for testing theories of galaxy formation and evolution that make predictions about how galaxies should develop in the absence of environmental effects. By comparing void galaxies to cluster galaxies of similar mass, astronomers can isolate the effects of environment from the effects of internal properties. Understanding which features of galaxies reflect nature and which reflect nurture, the void galaxy continues its quiet evolution through cosmic time, forming stars at a steady pace spinning through the darkness, growing slowly through the accumulation of its own recycled gas, without input from the larger universe. Its isolation has shaped every aspect of its history and will continue shaping its future as the universe ages and the voids grow emptier still. The properties we observe in void galaxies directly reflect this isolated development. The physical appearance of void galaxies differs from galaxies in denser environments in ways that reflect their isolated evolutionary histories and undisturbed development across cosmic time. These differences are subtle but measurable, revealing the effects of environment on galaxy properties through careful comparison between void dwellers and their counterparts in walls, filaments, and clusters. The void galaxy carries the signature of its solitude in its structure, its colors, and its ongoing activity. Color provides one of the most immediate indicators of galaxy properties, reflecting the ages and temperatures of the stellar populations that produce the light we observe. Blue galaxies contain young, hot, massive stars that burn bright and blue before dying quickly in supernova explosions or other energetic endings. Red galaxies contain older, cooler stars, their young stellar populations having died out long ago, leaving only the long-lived red and orange stars that persist for billions of years. Void galaxies tend toward the bluer end of the color spectrum, their stellar populations younger on average than galaxies of similar mass in denser environments. This blue color indicates ongoing star formation, the continued birth of new stars from gas clouds that have not been stripped or heated by environmental processes. The void galaxy is still actively building itself, adding new stars to its population even after billions of years of cosmic evolution. Cluster galaxies, by contrast, are often red and quiescent, their star formation having ceased billions of years ago due to various environmental processes that removed or heated their gas supply. These red and dead galaxies no longer form new stars at significant rates. Their light dominated by the ancient stellar populations that formed during earlier, more active epochs of their histories. The contrast between blue void galaxies and red cluster galaxies reveals the importance of environment in determining galactic fate. The ongoing star formation in void galaxies manifests in other observable properties beyond color, including emission lines in their spectra that indicate the presence of hot, ionized gas around young stars. These emission lines, particularly hydrogen alpha emission at a characteristic red wavelength, reveal regions where new stars are being born, and ultraviolet radiation is exciting the surrounding gas. Void galaxies show strong emission lines, indicating vigorous, ongoing star formation. The gas content of void galaxies supports their continued star formation, with void dwellers typically containing higher fractions of cold hydrogen gas relative to their stellar mass compared to galaxies in denser environments. This gas has not been stripped by cluster medium or consumed by triggered starbursts from interactions, remaining available as fuel for star formation over cosmic timescales. The void galaxy has preserved its gas supply through isolation. The shapes of void galaxies also reflect their undisturbed histories, with spiral galaxies in voids typically showing more regular and symmetric structure than similar spirals in crowded regions. The spiral arms extend smoothly from the galaxy center, without the distortions and asymmetries that tidal interactions produce, wrapped around the nucleus in textbook patterns of spiral structure. The disk remains thin and extended, without the thickening that mergers can cause. Void spiral galaxies often represent the clearest examples of pure spiral structure, the forms that theory predicts for rotating disk galaxies evolving under their own gravity without external perturbation. Their arms trace density waves that propagate through the disk, patterns of compression that trigger star formation as gas clouds encounter the wave and collapse under the enhanced pressure. This process continues smoothly in void galaxies without interruption. The sizes of void galaxies tend to be somewhat smaller than similar galaxies in denser regions, reflecting the absence of merger-driven growth that adds mass and size to galaxies through the accumulation of absorbed companions. Without mergers, void galaxies grow only through the gradual accretion of gas and the internal conversion of gas to stars, a slower process than the rapid growth that merger-rich histories provide. The void galaxy is smaller because it has had fewer opportunities to grow. This size difference is not dramatic, but is statistically significant when comparing populations of void galaxies to populations of field or cluster galaxies of similar types. A void spiral might be 10 or 20% smaller than an average spiral in a denser environment, a modest difference that nonetheless reflects the different evolutionary paths these galaxies have followed since their formation in the early universe. The dark matter halos surrounding void galaxies may also differ from those around galaxies in denser regions, though these differences are harder to measure directly since dark matter does not emit light. Theoretical models suggest that void galaxy halos are less massive relative to the stellar mass they contain, and that they have different density profiles, reflecting the different accretion histories that void environments produce. The void galaxy sits in a smaller, less concentrated dark matter halo. The stellar populations within void galaxies, when examined in detail through spectroscopy that reveals chemical compositions and ages, show signatures consistent with their undisturbed evolutionary histories. They contain somewhat lower proportions of heavy elements produced in supernova explosions, reflecting lower overall rates of star formation and chemical enrichment over cosmic time. The void galaxy has processed less gas through stars than a comparable galaxy in a merger-rich environment. These chemical differences are subtle but measurable with modern spectroscopic techniques that can determine the abundances of various elements in the atmospheres of stars across an entire galaxy. The lower metallicity of void galaxy stellar populations indicates that fewer generations of stars have lived and died within these systems, recycling their processed material into new stellar generations over the galaxy's history. The outer regions of void galaxies may extend to larger radii relative to their central brightness than galaxies in dense environments, their disk edges untruncated by tidal stripping from nearby companions. In cluster environments, the outer edges of galaxy disks are often truncated, their loosely bound stars stripped away by tidal forces from the cluster's collective gravity. Void galaxies retain their outer stars, which have never experienced such stripping forces. The rotational velocities of void galaxies follow patterns similar to other spiral galaxies of comparable mass, indicating that their internal dynamics are governed by the same physical processes regardless of external environment. The rotation curves rise from the center outward before flattening at larger radii, a signature of the dark matter halos that contain most of the galaxy's mass. This internal structure is universal. The combination of all these properties creates a portrait of void galaxies as undisturbed, gas-rich, star-forming systems that have evolved according to their own internal clocks, without environmental influence. They are younger in stellar population, bluer in color, more gas-rich, more regularly shaped, and slightly smaller than comparable galaxies in denser environments. Their properties directly reflect their cosmic addresses. Among the void galaxies that astronomers have identified and studied, certain individuals stand out as particularly extreme examples of cosmic isolation. Galaxies so far removed from any neighbor that they have become symbols of what loneliness means at cosmic scales. These exceptionally isolated galaxies provide the clearest test cases for understanding how environment shapes galaxy evolution, representing the far end of the isolation spectrum, where external influence approaches zero. MCG plus 01 minus 02 minus 015 has been called the loneliest galaxy in the observable universe, a designation that captures its extraordinary isolation within one of the deepest known cosmic voids. The galaxy sits alone in a vast empty region, with no significant neighbor for over 100 million light-years in any direction from its position. It has existed in this isolation for billions of years, evolving entirely according to its own internal dynamics, without external influence. The name of this lonely galaxy comes from its catalog designation, a string of numbers and letters that astronomers use to identify objects in systematic surveys, rather than a poetic name befitting its solitary nature. Located roughly 300 million light-years from Earth, in the direction of the constellation Pisces, it appears as a faint smudge in deep telescope images, unremarkable except for its extraordinary cosmic context. Its loneliness is not visible directly, but becomes apparent only when mapping the surrounding region. The galaxy itself is a spiral, with arms of stars curving around a central bulge in patterns similar to our own Milky Way and billions of other spiral galaxies throughout the universe. It continues forming stars from its gas supply, showing the blue colors and emission lines that indicate ongoing stellar birth, despite its isolation. In its internal properties, the galaxy resembles other void dwellers, distinguished primarily by the exceptional emptiness of its surroundings. The void containing this lonely galaxy represents one of the emptiest known regions of space, a bubble of low density that extends for vast distances before encountering the walls of galaxies that bound it on all sides. This void is not merely underdense, but dramatically so, containing far fewer galaxies than comparable volumes in other parts of the universe. The lonely galaxy exists at or near the center of this emptiness. Other exceptionally isolated galaxies have also been identified through systematic surveys that map the distribution of galaxies across large volumes of space. ESO 461-36 represents another well-studied example, a spiral galaxy in the southern sky that exists in profound isolation within its own cosmic void. Like MCG plus 01 minus 02 minus 015, it has developed independently, its properties reflecting undisturbed evolution. VGS 31 has been studied as part of the Void Galaxy Survey, a systematic effort to identify and characterize galaxies within known cosmic voids throughout the observable universe. This survey has catalogued thousands of void galaxies, providing statistical information about how isolation affects galaxy properties across the population rather than in individual exceptional cases. Each void galaxy in the survey contributes to our understanding of environmental effects. The discovery of these isolated galaxies requires mapping the positions of millions of galaxies across large volumes of space, identifying the voids as negative structures where galaxy counts drop below average, and then locating the sparse populations that exist within these empty regions. This is labor-intensive work, requiring large surveys and careful analysis, but it has revealed the diversity of isolation that exists throughout the cosmic web. The loneliest galaxies are found near the centers of the largest voids, where isolation reaches its maximum and the distance to the void walls is greatest from any direction. Galaxies near void edges are less isolated, experiencing some gravitational influence from the approaching wall, even if not yet fully embedded within the denser structure. The most isolated galaxies are those that sit at the hearts of the emptiest regions. An intelligent species arising within such a galaxy would have a very different view of the universe than we experience from our position within the relatively crowded local group. Looking outward from their galaxy, they would see almost nothing, the vast void extending in every direction without the companion galaxies that populate our sky. Their understanding of the universe would develop differently as a result. The nearest galaxies would be so distant that detecting them would require powerful telescopes, far beyond the naked eye visibility of the Andromeda galaxy from Earth. The very concept of other galaxies might remain theoretical until technology advanced enough to reveal the distant walls of galaxies bounding the void. The universe would seem emptier and lonelier from this perspective. These exceptionally isolated galaxies also provide the cleanest tests of theoretical predictions about galaxy evolution in the absence of environmental effects. Because their isolation is so extreme, any environmental influence is negligible, and their properties can be compared directly to models of pure internal evolution. The agreement between observation and theory supports our understanding of the physics that governs galaxy development. The void containing the loneliest known galaxy will continue to expand as the universe ages, stretching the already vast distances to even greater emptiness over billions of years. The galaxy itself will continue forming stars from its gas supply until that supply is exhausted through conversion to stars and lost through stellar winds and supernova explosions. Eventually, star formation will cease and the galaxy will fade, its stellar population aging and reddening over cosmic time. The isolation of these galaxies extends across time as well as space, their past histories as lonely as their present circumstances, because the voids have been empty throughout most of cosmic history. The lonely galaxy has never known close neighbors, never experienced the gravitational interactions that shape galaxies in crowded regions, never witnessed the cosmic traffic that galaxies in the web observe routinely. Its loneliness is permanent. The future of these galaxies is even greater isolation, as dark energy drives accelerating expansion and stretches the cosmic web to ever greater dimensions. The walls of galaxies surrounding their voids will recede faster than light can travel between them, eventually passing beyond the cosmic horizon and disappearing from view entirely. The loneliest galaxy will become lonelier still. Studying these extreme cases reveals what is possible at the edges of cosmic environmental diversity, the endpoints of a spectrum that extends from the densest cluster cores to the emptiest void interiors. Most galaxies fall somewhere between these extremes, but the extreme cases define the boundaries and clarify what environment can and cannot do to shape galaxy properties. The loneliest galaxies tell us about the limit of isolation. The existence of such isolated galaxies also raises questions about the meaning of cosmic community and connection across distances that dwarf everything in human experience. These galaxies are part of the same universe as all others, governed by the same physics and embedded in the same cosmic history, yet separated from almost all other matter by gulfs that nothing can cross within any reasonable timescale. The discovery of cosmic voids and the lonely galaxies within them emerged gradually through the 20th century, as astronomers developed the technology and conducted the surveys necessary to map the large-scale structure of the universe across volumes large enough to reveal its patterns. Early astronomers assumed that galaxies were distributed more or less uniformly throughout space, scattered randomly like raisins in a cosmic pudding, without large-scale organization. This assumption would prove dramatically wrong. The first hints of cosmic structure appeared in the distribution of nearby galaxies. Clusters of galaxies that stood out against the general field population as concentrations of many galaxies in small volumes. The Virgo cluster, the nearest large galaxy cluster to our position, was recognized early as an overdense region containing thousands of galaxies, where the general field might contain only dozens. These clusters suggested that galaxies were not randomly distributed. As surveys extended to greater distances and mapped more galaxies, the clustering became more apparent, with filaments and walls of galaxies stretching across the sky in patterns that suggested large-scale organization. The distribution was not uniform but clumpy, with some regions containing many more galaxies than average, while others contained correspondingly fewer. The structure of the cosmic web was beginning to emerge. The redshift surveys of the 1970s and 80s transformed our understanding of cosmic structure by providing three-dimensional maps of galaxy distribution rather than the two-dimensional projections that earlier surveys had produced. By measuring the redshift of each galaxy, astronomers could determine its distance from us and place it in a three-dimensional volume, revealing the full structure of the cosmic web for the first time. The Center for Astrophysics Redshift Survey, published in 1986, provided a dramatic visualization of cosmic structure that shocked many astronomers who had expected more uniform distribution. The map showed galaxies arranged in thin walls and filaments surrounding vast, empty regions, where almost no galaxies appeared. The cosmic web was far more structured than most had anticipated. The Boötis void was among the first great empty regions to be recognized, a roughly spherical bubble of low galaxy density spanning approximately 330 million light-years in the direction of the constellation Boötes. Discovered in 1981 by Robert Kirshner and colleagues, the void contained only about 60 known galaxies, despite its enormous volume, far fewer than comparable regions in denser parts of the universe. The initial reaction to the Boötes void included skepticism that such a large empty region could actually exist, as it challenged prevailing expectations about cosmic uniformity. Some astronomers wondered whether the void was real, or an artifact of incomplete surveying, a region where galaxies existed, but had not yet been detected. Further observations confirmed that the void was genuine, a vast bubble of true underdensity. The discovery of multiple voids throughout the mapped universe established that these empty regions were not exceptional, but common, comprising much of the universe's volume and representing a fundamental feature of cosmic structure rather than isolated anomalies. The voids were everywhere, separated by the walls and filaments where most galaxies gathered, but dominating the universe by volume nonetheless. The Sloan Digital Sky Survey, beginning in 2000, provided the most detailed maps of cosmic structure to date, surveying millions of galaxies across a significant fraction of the observable universe. These maps revealed the cosmic web in unprecedented detail, showing the voids as clearly as the walls and filaments. The full structure of the universe laid out in 3 dimensions for analysis and contemplation. The void galaxies appeared in these surveys as the sparse populations within the empty regions, galaxies that had formed despite the underdensity of their environments and persisted despite the lack of nearby companions. Identifying these void galaxies required first identifying the voids themselves, defining their boundaries, and then locating the galaxies that fell within those boundaries. Systematic catalogues of void galaxies emerged from this work. The Void Galaxy Survey represented a dedicated effort to study the properties of void galaxies as a population, comparing them to control samples of galaxies in denser environments to identify the effects of isolation on galaxy evolution. This survey and others like it established that void galaxies differ systematically from their counterparts elsewhere. Bluer, more gas-rich, and more actively star-forming on average. The discovery process continues today as new surveys map ever larger volumes of the universe with ever greater sensitivity, revealing smaller voids and fainter galaxies that earlier surveys missed. Each new survey adds to our understanding of cosmic structure and the populations that inhabit different environments. The voids remain a focus of active research. Computer simulations have complemented observational surveys in understanding the formation and properties of cosmic voids and the galaxies within them. These simulations modeled the gravitational evolution of matter from the early universe to the present, producing virtual universes that can be compared to observations. The simulated universes contain voids and void galaxies that match the observed populations well. The agreement between simulation and observation supports our theoretical understanding of how voids form and evolve, confirming that the observed structure can be explained by known physics operating over cosmic time. The simulations also allow predictions about void properties that observations have not yet tested, guiding future survey strategies and observational programs. The discovery of cosmic voids changed our picture of the universe fundamentally, revealing that most of space is empty and that galaxies concentrate in a web-like structure rather than filling space uniformly. This insight emerged gradually through decades of observational work, theoretical development, and technological advancement that made ever larger surveys possible. The void galaxies that emerged from this discovery represent a population unlike any other. Isolated systems that have evolved independently of the cosmic environment that shapes most galactic evolution. Their study continues to provide insights into the physics of galaxy formation and evolution, testing theories in the cleanest possible environments, free from the complications of crowded cosmic neighborhoods. Observing void galaxies presents unique challenges that differ from the challenges of observing galaxies in denser environments, requiring strategies adapted to the sparse populations and vast empty regions that characterize these underdense cosmic volumes. Astronomers have developed techniques specifically suited to finding and studying the lonely inhabitants of the voids, revealing their properties through careful observation and analysis across multiple wavelengths. The first challenge in studying void galaxies is finding them, identifying which galaxies inhabit voids rather than the walls, filaments, or clusters that contain most of the galactic population. This requires mapping the surrounding cosmic structure first, determining where the voids lie and where their boundaries fall, before identifying the galaxies that exist within those boundaries. The void galaxies reveal themselves as isolated points in the mapped distribution. Large-scale redshift surveys provide the data necessary for this identification, measuring the distances to millions of galaxies and placing them in three-dimensional space, where the voids become apparent as regions of low galaxy density. Computer algorithms then identify the void boundaries and catalog the galaxies within them, creating samples that can be studied as populations or observed individually for detailed characterization. The Void Galaxy Survey and similar projects have produced catalogs containing thousands of void galaxies, far more than can be studied individually in detail, but sufficient for statistical analysis of population properties. By comparing the average properties of void galaxies to control samples from denser regions, astronomers can identify how environment affects galaxy evolution across the population. Individual void galaxies of particular interest, such as the loneliest known examples, receive more detailed attention through targeted observations with powerful telescopes. These observations might include deep imaging to reveal the galaxy's structure, spectroscopy to measure its stellar populations and gas content, and observations at multiple wavelengths from radio to X-ray to capture the full range of physical processes occurring within. Infrared observations reveal the older stellar populations in void galaxies, stars that emit most of their light at longer wavelengths than the blue young stars that dominate the visible appearance. The infrared also penetrates dust that might obscure parts of the galaxy at shorter wavelengths, revealing the full extent of the stellar distribution. Space telescopes, like Spitzer and now James Webb, have provided infrared observations of void galaxies. Ultraviolet observations reveal the youngest, hottest stars in void galaxies, the massive blue stars that form most recently and burn through their fuel quickly before dying in supernova explosions. The ultraviolet light indicates ongoing star formation, confirming that void galaxies remain actively building new stellar populations despite their isolation. The Galax satellite provided ultraviolet surveys that included many void galaxies. Radio observations detect the cold hydrogen gas that provides the fuel for star formation, the neutral atomic hydrogen that fills the disk of spiral galaxies and collapses into stars in dense regions. Void galaxies often contain substantial reservoirs of this gas, consistent with the absence of environmental processes that strip gas from galaxies in denser environments. Radio telescopes have mapped the gas content of many void galaxies. The 21-centimeter emission line of neutral hydrogen provides a particularly valuable probe of void galaxy gas content emitted by hydrogen atoms throughout the gas disk and detectable with radio telescopes across cosmic distances. The strength of this emission indicates how much gas the galaxy contains, while its distribution across the galaxy reveals the spatial extent of the gas reservoir. Large surveys have detected this emission from thousands of void galaxies. Spectroscopy at optical wavelengths reveals the detailed properties of stellar populations in void galaxies, including their ages, chemical compositions, and ongoing star formation rates. By analyzing the spectrum of light from a galaxy, astronomers can determine what types of stars contribute to the light and how those stars differ from populations in other environments. This analysis confirms the distinctive properties of void dwellers. The emission lines in void galaxy spectra reveal the presence of ionized gas surrounding young stars, regions where ultraviolet radiation from hot stellar surfaces has stripped electrons from hydrogen atoms. The strength of these emission lines indicates the rate of star formation, with stronger lines indicating more young stars producing more ionizing radiation. Void galaxies show strong emission lines consistent with ongoing star formation. Deep imaging reveals the detailed structure of void galaxies, their spiral arms, bulges, and disk components visible when observed with sufficient depth and resolution. The regular, undisturbed appearance of void spirals confirms their lack of recent interactions, their structure reflecting pure internal dynamics rather than external perturbation. The imaging also reveals the extent of the stellar distribution. Gravitational lensing observations can probe the dark matter halos of void galaxies, using the bending of light from background sources to map the mass distribution that surrounds the visible galaxy. These observations are challenging for individual galaxies, but can provide statistical constraints on halo properties when applied to populations. The dark matter in void galaxies remains less well characterized than other properties. The observational study of void galaxies continues to advance as new telescopes and surveys come online, providing ever more detailed views of these isolated systems. The Vera Rubin Observatory will soon begin surveying the sky at unprecedented depth, identifying millions of new void galaxies for statistical study. Future spectroscopic surveys will measure the properties of these galaxies in detail. Each observation adds to our understanding of how isolation shapes galaxy evolution, testing theoretical predictions against the cleanest observational samples available. The void galaxies serve as control experiments in the cosmic laboratory, systems where environment can be effectively set to zero, and internal physics dominates the observable properties completely. The observational challenges are worth the effort because void galaxies provide insights unavailable from any other galaxy population. Views of pure evolution, uncontaminated by the environmental effects that complicate interpretation of galaxies in denser regions. Their isolation, which makes them hard to find, also makes them scientifically valuable once found and characterized. The future of void galaxies, and the voids themselves, extends into timescales that dwarf everything in human experience. Billions and trillions of years, during which the universe will continue to evolve, and the isolation of void dwellers will deepen beyond anything observed today. The cosmic expansion that has shaped the universe since its beginning will continue, driven by dark energy that accelerates the separation between distant structures across the cosmic web. Dark energy represents the dominant component of the universe's energy content today, comprising roughly 68% of the total and driving accelerating expansion that will reshape cosmic structure over the coming eons. This mysterious force, whose nature remains unclear despite decades of study, acts to push space apart, counteracting the gravitational attraction that would otherwise slow the expansion. In voids where gravity is weakest, dark energy dominates most strongly. The voids have been growing throughout cosmic history as matter flows toward denser regions and dark energy stretches the already underdense bubbles to ever larger dimensions. This growth will continue and accelerate as dark energy becomes ever more dominant over the matter content of the universe. The voids of the future will be larger and emptier than the voids of today. Void galaxies will become more isolated as their surrounding voids expand, the distance to the nearest walls and filaments increasing over time as space stretches between them. A galaxy that currently sits 100 million light-years from the void edge will find that distance growing to 200 million, then 500 million, then billions of light-years as cosmic expansion proceeds over the coming billions of years. The cosmic web itself will stretch and thin, the walls becoming more attenuated and the filaments more tenuous as the expansion spreads matter ever more sparsely through the growing volume of space. The dense concentrations that currently characterize the web will become less dense, the contrasts between voids and walls diminishing as both approach the ever-decreasing cosmic average density. Eventually, on timescales of trillions of years, the structures of the cosmic web may become so attenuated that they effectively disappear, merged into a general sparseness that characterizes all of space rather than distinct voids and walls. The void galaxies of today may find themselves no more isolated than any other galaxies, because all galaxies will have become isolated by the expansion of space. Before this ultimate fate arrives, the void galaxies will experience ever-deepening isolation as the cosmic web recedes beyond their observable horizons. The walls of galaxies currently visible from within a void will redshift as they recede, their light stretching to longer and longer wavelengths until it fades from view entirely. The void galaxy's observable universe will shrink. The cosmic horizon defines the boundary beyond which light cannot reach an observer, because the expansion of space carries it away faster than it can travel toward them. As expansion accelerates, this horizon will contract, enclosing a smaller volume of accessible universe. The void galaxy will lose its view of the cosmic web, the distant walls disappearing beyond the shrinking horizon, one by one. Within the void galaxy itself, stellar evolution will continue through these eons, stars being born from gas, living out their lives, and dying in various ways depending on their masses. The gas supply will gradually deplete as it converts to stars, and as stellar winds carry processed material away from the galaxy. Star formation will eventually cease when the gas is exhausted. After star formation ends, the existing stellar population will age, the massive blue stars dying first, followed by progressively smaller and longer-lived stars over billions of years. The galaxy will redden as its stellar population ages, its light dominated by ever older, ever cooler stars that burn their fuel ever more slowly. The void galaxy will become a red and dead remnant. The final stage of stellar evolution in the void galaxy will see only the smallest red dwarf stars still shining, their lifespans measured in trillions of years. their dim red light barely illuminating the space around them. These stars will persist long after the sun has died, long after the Milky Way has merged with Andromeda, outlasting almost everything else in the universe through their slow and steady burning. Eventually, even these longest-lived stars will exhaust their fuel, their nuclear fires dying out as the last hydrogen fuses to helium and no more energy can be extracted. The void galaxy will go dark, its stellar population becoming a collection of stellar remnants, white dwarfs and neutron stars and black holes, slowly cooling through the eternal night of the far future universe. The dark matter halo surrounding the void galaxy will persist even after the stars have died, the invisible matter continuing to define the gravitational well in which the stellar remnants orbit. This dark matter will continue orbiting as it has for billions of years, unchanged by the death of the stars it surrounded, patient and persistent through the aging of the cosmos. The void galaxy's isolation will have reached its ultimate expression by this far future epoch, surrounded by emptiness that extends beyond any horizon, its neighbors long since receded beyond the reach of light. It will exist in perfect isolation, the loneliness it experienced in earlier cosmic epochs, having deepened to complete separation from everything else that might still exist elsewhere in the expanding void. This future is common to all galaxies, not just those in voids, as cosmic expansion will eventually isolate every structure from every other structure, regardless of where they currently sit in the cosmic web. The void galaxies simply preview this future, their current isolation foreshadowing the ultimate isolation that awaits all cosmic structures in the infinitely expanding cosmos. The contemplation of this far future provides perspective on the cosmic scales of time and space that characterize our universe, scales on which human concerns become invisible and cosmic evolution proceeds through processes that care nothing for the fleeting presence of intelligent observers. The void galaxies drift through this cosmic time, patient and undisturbed, their isolation a preview of the universal fate. The loneliest galaxy drifts through its void tonight, as it has drifted for billions of years before any human eye looked upward at the stars, spinning slowly in the darkness with its spiral arms wrapped around its ancient core. The void surrounds it in every direction, emptiness extending for distances that would take light itself 100 million years to cross, a darkness broken only by the faint and impossibly distant glow of the cosmic web that bounds this empty region. The galaxy exists in cosmic solitude, separated from its nearest significant neighbor by gulfs that dwarf everything in ordinary human experience. This isolation is not lonely in the human sense of emotional distress. For galaxies do not feel, and the void is simply the environment in which this galaxy has always existed throughout its billions of years of cosmic life. The galaxy formed in this sparse region of the early universe, surviving as its surroundings emptied out, evolving according to its own internal dynamics, without interference from neighbors or the gravitational interactions that shape galaxies in denser regions. Its solitude is simply its nature. Stars continue to form within this lonely galaxy, collapsing from gas clouds in the spiral arms and igniting nuclear fusion that will sustain them for millions or billions of years, depending on their masses. The stellar cycle of birth, life, and death proceeds here, as it proceeds in every galaxy throughout the cosmos, governed by physics that operates identically regardless of cosmic address. The void galaxy remains alive and active despite its isolation. The view from within this galaxy would reveal a night sky unlike any we experience from Earth. The stars of the home galaxy scattered overhead in familiar patterns, while the intergalactic darkness beyond shows almost nothing at all. No neighboring galaxies would be visible to the naked eye. No Andromeda appearing as a smudge in the darkness. No Magellanic clouds providing cloudy companions in the sky. The universe would seem emptier from this vantage point. An intelligent species arising within such a galaxy might develop very different ideas about the cosmos than we have developed from our position in the relatively crowded local group. They might initially believe themselves alone in the universe, their galaxy, the only island of matter in an infinite sea of darkness. The discovery of other galaxies would require sophisticated technology and would represent a revelation of cosmic proportions. Yet this lonely galaxy remains connected to the larger universe, despite its isolation, embedded in the same cosmic history, governed by the same physical laws, composed of the same elements that exist everywhere in the cosmos. The light from the cosmic microwave background reaches even this isolated system, bringing news of the hot early universe when matter was distributed more uniformly. The void galaxy is alone, but not separate. The cosmic web that bounds the void can be observed from within. Distant walls of galaxies appearing as faint concentrations of light at the limits of detection. These walls mark the boundaries of the void, the places where matter concentrated during the billions of years of cosmic structure formation, while this region emptied out. The void galaxy can see that it is not alone in the universe, even if its neighbors are impossibly far away. The void itself represents a fundamental feature of cosmic structure, one of the great empty bubbles that fill most of the universe's volume while containing little of its matter. These voids are as much a part of the cosmic web as the walls and filaments where most galaxies gather, defining the structure through their absence as surely as the galaxies define it through their presence. Emptiness is not nothing, but is a specific and important feature of cosmic organization. The study of void galaxies has revealed how environment shapes galaxy evolution, showing that isolation produces distinct properties that differ systematically from galaxies in crowded regions. The void dwellers are bluer, more gas-rich, more regularly shaped, and more actively star-forming than their counterparts in clusters and walls. Their properties reflect their undisturbed histories, billions of years of evolution without external interference. The future holds greater isolation still for these lonely galaxies as the universe continues to expand, and dark energy drives accelerating separation between distant structures. The voids will grow, the walls will recede, and the void galaxies will find themselves ever more alone in the expanding cosmos. The isolation they experience today is mild compared to what the far future will bring. Yet the void galaxy continues its slow rotation through the darkness, patient and unhurried, its stars shining into the void without concern for whether anyone observes their light. The galaxy has existed for billions of years and will continue for billions more, its isolation neither burden nor blessing, but simply the circumstance of its cosmic existence. It is what it is. The contemplation of such cosmic loneliness provides perspective on our own cosmic situation. Inhabitants of a relatively crowded neighborhood who can look up and see companion galaxies with the naked eye. We are not isolated as the void galaxies are isolated. surrounded instead by dozens of nearby companions and embedded in a cosmic web that connects us to larger structures, extending across the observable universe. The void galaxies remind us that most of space is empty, that the matter content of the universe concentrates in a web-like structure, leaving vast bubbles of near-nothingness between the strands. Our experience of a relatively crowded cosmic neighborhood is not typical, but exceptional, the consequence of our location in a filament rather than a void. Other perspectives on the universe exist. The loneliest galaxy spins on through its void, forming stars from gas clouds, spinning through the darkness, evolving according to its own internal rhythms, without external interference. It has never known close neighbors and never will. Its cosmic address determined by conditions in the early universe that placed it in a region destined to become empty. This is its home. The universe contains both the crowded clusters where thousands of galaxies jostle together, and the empty voids where lonely spirals drift in isolation, both extremes part of the same cosmic structure that emerged from the nearly uniform early universe through billions of years of gravitational evolution. The diversity of cosmic environments reflects the physics of structure formation operating on initial conditions set in the first moments after the Big Bang. The void galaxy asks nothing of the universe and receives nothing from it, existing independently in a way that no galaxy in a dense environment can achieve. Its evolution is pure, undisturbed, a clean experiment in galaxy formation that theorists can compare to their models without the complications that crowded environments introduce. The isolation that defines it also makes it valuable. Tonight, the loneliest galaxy continues its ancient journey through the void, unchanged by our awareness of it, spinning as it has spun for billions of years. The void stretches around it in silent emptiness. The cosmic web glows faintly at impossible distances, and the galaxy drifts onward through the darkness, patient and alone, a spiral of light in the vast cathedral of cosmic structure, the loneliest galaxy in the universe.